Now, because Numpy uses the notation that we're familiar with from linear algebra, let's do a quick review of many linear algebra operations, and at the same time, let's go through and see what the Numpy equivalents of those operations are and the syntax for using those different operations. So what I've done here is I've opened up a Python notebook called Unit4 Optimize. And what we're eventually going to build up to is how to put together a matrix of feature values and a vector of values that we want to predict, and try to find the parameters of a curve where we can fit the x data to some y data that we'd like to predict. But before doing that, let's first build up our linear algebra operations. So let's say that we have a matrix A. And so the matrix A that we have here is actually, the matrix A that we have is going to be, looks like this, where the top row is 0, 1, 2, and the bottom row is 3, 4, 5. Now, if we want to represent that in Numpy, it's as simple as giving two Python lists of numbers to the np.array function. Now, if you look at the syntax, there's two lists. There's a list with 0, 1, 2, which I want to be the first row, and then a second row, which is 3, 4, 5. Now, each of those are actually placed inside of an even bigger Python list, if you'll notice the brackets on the outside there. So this is actually a Python list of lists. When Numpy sees that, it figures, okay, you want a two-dimensional matrix. So if I were to print out the values of this matrix, it would actually print out this. So under the hood, this is a Numpy array of 0, 1, 2, 3, 4, 5. So there are 2 rows, 3 columns. It's 2 by 3. If I perform a transpose operation on this matrix, so if each of the elements inside of this matrix were going to be denoted as, let's say, A11, which means A in the first row, first column, A12, which means A in the first row and the second column, right here. If we want to define a transpose operation, really what we're doing here is we are taking the first row and we're going to make that into the first column of the matrix. So we're actually just kind of transferring this and transposing it such that this row becomes this column and this row becomes this column. So great. So typically when we do that, we write this as A, and then we almost put it like a capital T index upon A, like a superscript. So in Numpy, what we do is we say A dot capital T, and that's the transpose of the matrix. And if we were to print out the values of that, we can see that we have actually switched out the rows and the column format. So the shape of this would now be 3 by 2. There's also a flattening operation. So many times we want to take all of the values that we have inside of this matrix notation and simply represent it as one long flattened vector. And the way that Numpy does that is when we call a.flatten, it assumes that, okay, I'm going to take the exact first row, and those will be the first elements in the column that I have. Now, to flatten this, what I'm going to do is I'm going to take the second row that I have right here, and I'm actually just going to place it up next to it, right? So if we were to look at this, we actually now have one big long vector with the values A11, A12, A13, and now we just concatenate the second row upon that. And so if we were to actually do this with other values, so if we had a matrix that was, say, the transpose of this, which was 3 by 2, the flattening operation would just go row by row and concatenate everything together. So if we were to do a flattening operation on A transpose, what we'd have is A transpose. If we want to flatten that, that's going to go out to, we'll have A11 and A21, and then we'll have the second row on this, so we'll take A12 and A22, and then we'll take the very last row that's inside of A, and it'll become here, and so now we have one big vector right here, which consists of all of the rows concatenated together. So concatenation is also a really important operation because it's how we can add features or add observations to a given matrix that we have of, say, feature data. So Numpy has a lot of built-in concatenation operations. The first one, let's say we wanted to concatenate 3 different matrices, and these are all vectors, right? So A, the first one, is going to be just a single row by 2 columns, so it's a 1 by 2 matrix. B is going to be a 1 by 4 matrix, and C is going to be a 1 by 3 matrix. So when I actually want to concatenate those together, the resulting matrix, let's say D is the resulting matrix that I want to have. Well, what I really want to have is a matrix that has A concatenated with B concatenated with C. And that's because each of these have the same number of rows. So it's really, I can only row concatenate these together. The way that I tell Numpy to do that is I put A, B, and C inside of a tuple. Right? So A, B, and C, they're just Numpy arrays. I put them in a tuple, which means I put these parentheses around this tuple, and that makes it a single input variable into the function np.concatenate, right? So the concatenate function part of Numpy. And I haven't told Numpy how I want to concatenate these together, so it says, oh, well, they all have a common dimension, they all have one row, let me just stack all of these together into one single row, and that's exactly what I wanted it to do. Well, now let's look at a case where I have something a little more complicated. Let's say A and B are both 2 by 2 matrices, right? So A is a 2 by 2 matrix, and B is a 2 by 2 matrix. Now, if I just use the generic concatenate function right here, essentially it's just going to concatenate A and B on top of one another into one single matrix right here. But there were actually multiple options that I could concatenate this matrix with. And so when I say concatenate and I give it a tuple of AB, Numpy just assumes that I want to do it on the very first dimension. It's just going to stack them vertically, right? But I could have also stacked them horizontally, right? Such that I stacked A and B together to make one big matrix here, where each of these are 2 by 2. And so the syntax for if I want to explicitly tell Numpy how to concatenate things together, I can still call the concatenate function, but now I'm going to say axis equals 0, right? And so what that means is that I want to stack these vertically together on top of one another. But if I say axis equals 1, that means I want to stack these horizontally on one another like that. So this is what's typically known as row concatenation and column concatenation, which means concatenating the columns on. So let's say that this was feature data that I had. Well, the difference between concatenating with axis equals 0, this one is adding more rows, so I'm adding new observations inside of my table, if each table is a new observation. Whereas concatenating with axis equal to 0, this would be like adding more features to the existing observations that I have. I have 2 observations, but now I have some more measurements for each of those observations that I can add in as features. So now let's talk about some things where we're going to get just a little more specific in what we can do with representing things internally as a matrix, right? So there are some things that we can do in Numpy because we can give things a new dimension. So let's say we have an array A, and the A array is just going to be equal to the array 1, 2, and 3 right here. And we simply represent that, and we can print it out with 1, 2, 3. Now, let's say we actually wanted to represent that as a column vector. Well, we can actually do something really, really simple here. We can tell Numpy that we want to add a new axis into the array. The syntax for doing that is going to be this right here. So what that says is I would like to take A and all of the rows, but what I would like to do is actually say that A, if I put this colon in here, what that essentially is doing is saying I would like all of the existing values in A to be part of the first column, right? And then what I'd like to do is add a new axis right here, which is the number of rows. And so what that actually does is it says A is equal to 1, 2, 3, right here. Because the original shape of A, when I just created it here, it just had a shape of 3 right there. It actually, it wasn't represented as a rows and columns. It just knew that there was a dimension 3. When I said that I wanted A, all of the existing data to stay the same, but then add a new axis on the outside, so A at the new axis, what that essentially did is said, oh, well, you want the existing dimensions to be 3, and then add a 1 dimension right here. So now I'm going to have 3 rows and 1 column. Right? And so that, the equivalent of that, is this over here. So when I print out the shape of A with a new axis on it, it's actually 3 by 1. And you'll notice here that as I'm doing this A at the np.new axis, it's not converting the object A. It's manipulating A and then returning a whole new object with A's values inserted here and a new axis added onto the end, which happens to be 1 column. So to make this maybe a little more explicit, let's look at B right here. Now, if you'll remember, B was not a column vector. B we had represented as 5, 6, and 7, and 8. It's what we concatenated on a 2 by 2 matrix here. So B is actually equal to 5, 6, 7, 8, right? 7. Now, what I'm doing right here is I'm going to say B at the new axis and all of the existing values. So what this syntax is saying is that I'd like to add a new dimension. So the dimensions that I have right now are, I could actually represent this 5, 6, 7, and 8. If I represented this, let's say as something like a block, 5, 6, 7, and 8, well, it doesn't really have, let's say this is the first dimension here, and this is the second dimension. Well, there's another dimension I'm saying that I want to add to this, and it's 3-dimensional now in the background. Let's say that this matrix now is 1 dimension this way, right? Even though it's 2 by 2 this way, I'm saying add a new dimension and make sure that that new dimension is the very first dimension. So what this is represented internally as is a 1 by 2 by 2 matrix. And if I wanted to, I could actually stack another 1 by 2 by 2 matrix onto this, and it would just be stacking. I could stack in this direction if I wanted to, or I could create new dimensions, let's say in this direction here, in this direction here, possibly added here. So now there's multiple dimensions that I can represent this. And Numpy is pretty generic in this format in that I can have an n-dimensional array. It doesn't matter how big it is. Now, typically with data science, we are concerned with 2, 3, maybe 4 dimensions if we're talking about images or batches of images together. But typically we're only concerned with 2 dimensions. And so the new axis that we're going to use is typically going to be used in something like this, where we want to take an existing row vector, turn it into a column vector using the new axis technique. Okay, great. So now let's go and let's actually do some interesting operations. Let's start using Numpy to perform some operations upon 2 different, let's say, vectors. And so we have an A vector here, which is 1, 2, 3. So A is equal to 1, 2, 3. And B is equal to 5, and then 2, and then 6. So Numpy interprets different operations differently. So if I wanted to add these 2 things together, well, I can just add them together. I'm just going to get 6, 4, and 9, right? I just go element by element and add them together. And that's exactly what happens if I say A plus B. A plus B gives me 6, 4, and 9. If I were to subtract the 2 from each other, I would get A minus B, so I would get -4, 0, and then 3 minus 6, -3. So that creates a new matrix where I've just gone element by element and then done the subtraction. Now here's where things get interesting. So Numpy has multiple ways that we can do multiplication. Now if you'll remember, multiplication of matrices is not simple element by element multiplication. However, Numpy supports element by element multiplication, and the element by element multiplication is actually just the asterisk. So if we say what we're used to calling multiplication, that is actually element-wise multiplication. So I multiply 1 by 5, and then I multiply 2 by 2, and then I multiply 3 by 6. And so on the output, when I do this a times b, I get 5, 4, and 18. It's not matrix multiplication, it's element-wise multiplication. So the same thing works for division. I would take each element divided by each element of a and b. They have to be the same size for these to work. I could do modulus. I can even take them to a power. And so b to the a, what that represents is taking 1, now a to the b, so 1 to the 5th power, 2 to the 2nd power, 3 to the 6th power, right? So element by element, I'm just inserting the elements of b as exponentials. And what I get with that is something where it's 5, 4, and 2 to the 16. So 216. If I really want to do matrix operations, I either have to call a special function, or I can actually use the @ symbol here to do multiplication. And this is something that's been overloaded in Python 3. So Python 2 doesn't support the @ symbol. You actually would have to write a function you can call np, and then the function is dot for dot product. And then I would give it a and b. Then it would actually return the dot product between these two vectors. Now, the dot product between these two vectors is actually doing for this, it's an element by element multiplication. And then I add up all of the values. So if I do an element by element multiplication and add them up, it's just adding 6 plus 4 plus 9 so that I get 27 on the output. But if you'll recall, matrix multiplication, when it's between vectors, can look a lot differently. So let's say we had a matrix A, and I'll represent this as a capital. And I'll call each of the rows, let's say A1 right here is the first row of A. Let's say A2 right here, it's another vector, and all the way down until I have A to the cap n. Now, if B is similarly represented, but now let me say here that B1, these are the columns of B, B2, all the way to B sub cap n. If I wanted to multiply A times B, take the dot product between them, well, what I would actually be doing is taking the first row of A multiplied by the first column of B, and that would get me my very first element of these. So I would multiply them together and then add them up right here. So this is the dot product between A1 and B1. The second element that I'm going to have right here would actually be A1 multiplied by B2. And then I add everything up inside of that column, and so on and so forth until I get all the way down over to here where I have A1 times B sub cap m. This one I have AN times B sub cap m. This one going all the way down this way, excuse me, I would have A sub n times B1 and adding them all up. And so what I get on the output is something with n number of rows by m number of columns. So I get an n by m matrix. Now, there's some interesting things that we can do in Numpy, and what they're known as broadcasting operations. And so that's when we try to do these different operations, such as maybe just addition, but we have different sized matrices for one another. So if I take A right here, and A happens to be a 3 rows by 2 columns, right? If I want to broadcast that, so A is 3 rows by 2 columns, 1, 2, 3, 4, 5, 6. B is actually just equal to -1, 3, like this. Now, when I try to, I can't directly do a subtraction. That operation is not supported. But let's say I wanted to broadcast the elements of B such that if I said A minus B right here, what I'm really trying to do is I want to repeat this B for each of the rows and then perform the subtraction or the addition operation. Let's say it's addition, right? And so what that would do, it was to say, oh, okay, well, what's 1, 2 plus -1, 3? And so the first elements that I would get would be 0 and 5. And then it's going to say, okay, well, what's -1, 3 added to 3, 4? And I would get 2 and 7. And then so on and so forth. We'll get 4 and 9 on the output here. And so what that is, that's known as a broadcasting operations, where if there's some possible way that it can take B and broadcast it into the dimensions of A, it'll go ahead and try to do that, right? And that's kind of a unique and interesting operation for Numpy. There's also some really, really efficient operations, some functions that we can call from NumPy that, because it's written in C++, they're actually more efficient to use the NumPy calculations than they are to typically do them in, say, Python. So let's say I had an array of all of these different numbers. Some of them are repeated. I can actually call np.unique and get the values on the output of each of these, where they come back in sorted order, and that's how it knows that things are unique. And this is a very, very quick operation, even for very large amounts of data, very large matrices. So now let's talk just a little bit about indexing in NumPy. So indexing is kind of an interesting operation here because a lot of times we'll want to index specifically into rows or columns of a given matrix that we might have. So let's say that we have a matrix A, and this matrix A is, let me just restart all of this right here. So this matrix A that we have right here, we'll define A as equaling 1, 4.5, and 1500. And it's got a couple of different rows. It's actually a 3 by 3 matrix. And then 2, 0.5, and 1300. Well, excuse me, indexing into this matrix is going to be something called slicing. And what I want to do is actually I'm pulling out slices of this matrix at a time. So if I wanted to grab, let's say, the very first column, the way that I would do that is I would actually use the colon operator. So I would say A at all of the rows and the 0th column right here. And what that actually does is it says, I don't care what the row value is, I don't care which row it's in, but I do care that everything is part of the 0th column. So that grabs this very first column right here. I can do the exact same notation here where it says, no, I want the 0th row, and I don't care about what are in the different columns that might exist right here. And so that would actually grab the 0th row of A, being 1, 4.5, and 1500. And so we can see that those are the exact supported operations that we have for this. And that actually gives rise to some interesting different things that we can do here. So let's go back a little and let's look at what we're going to do here is we're going to say we don't care which row, we want the 0th column greater than or equal to 2. Now, this is an interesting operation because what it does is it goes in and it grabs this as a vector and it says, where is that vector greater than or equal to 2? And it's false at the top. But then both of these elements right here, these are true. So internally, NumPy actually represents that as a logical vector, false, true, true. And if we actually print out the values of that, we get false, true, and true. And that's interesting because now we can actually use this. Let's call this just, this is like an IDX variable or something like that. We can use that to index into the matrix A. And the way that we would do that is we would say, oh, okay, well, where is A, the 0th column of A, greater than 2? Wherever that happens, that's when I want to index into A, right? And so when I index into that, it says, give me the rows of A where this was true. And so the only rows of A where that was true are these two right here. And so on the output, what I can see here is I'm only grabbing the rows of A where that was equal to true. That's a very powerful, very intuitive and succinct operation that I can perform for slicing different values and actually grabbing different rows. Like you can imagine if A was jumbled up to where there were different rows kind of scattered throughout this matrix that might be true, it would be able to just grab each of those rows out of the matrix where a certain column value was greater than another threshold or something that you had and create a whole new matrix really, really quickly. And again, this is a very efficient operation because it's written in C++. So now let's go here and actually perform a few operations that are very typical operations for matrices. And so what I'm going to do here is let's just redraw part of A right here. Right, so A had the values of 1, 5, and 2 as part of the first column that we had right here. So one of the operations that you can perform on a matrix, and that will become useful when we're performing optimization techniques, is going to be a trace operation. And a trace operation says, oh, okay, well, I want to go in and grab the diagonal of this matrix that I have right here, and I want to sum all the values up. So I would take 1300 plus 3.5 plus 1, and if I actually print out what the trace of A is, that's actually 1304.5. Right, so 3.5 and the 1 value. I can actually go in here and also grab, hey, what's just the diagonal of A? And what that does, the diagonal just creates a new vector, which is 1, 3.5, and 1300. So that creates a totally new vector that I have. So let's save that vector into a value of v. Let's say v is equal to whatever the diagonal is. When I take the sum of that, I should get exactly what I got from the trace operation, which I do. And I can actually, if I wanted to, I could create a new matrix where v is on the diagonal of the matrix. And so if I were to say, you know, this operation where I have diagonal of v, it creates a square matrix where the diagonal is 1, 3.5, and 1300, and every other element is equal to 0. And that can actually be an important operation when we are trying to do some of our optimization techniques, when we want a concise, when we want something concise, we'll do matrix multiplication, and things just work out a lot better when we actually put things on a diagonal and do the matrix multiplication. And again, this is a fully functional numerical package. Numpy has a lot of things built in for linear algebra, such as taking the determinant of a matrix. If you'll remember, taking the determinant of a matrix for a 2 by 2 matrix where we have A, B, C, and D right here, the determinant of this matrix is actually just we're multiplying the diagonal here and subtracting the multiplication of that diagonal. So it's actually equal to AD minus BC. And you may not remember determinants explicitly. They have a lot of different properties with looking at geometric interpretations of area and volume inside of different transformations that are described by a matrix. However, for us, we can really just remember that a determinant takes a matrix A and it figures out kind of what the scale of a transformation is applied to that matrix. And when we get to bigger matrices, we can still take the diagonal, we can still use the determinant of a 2 by 2 matrix to figure out what the determinant of a 3 by 3 matrix is, and so it builds on each of the others. You'll also remember that determinants are used to calculate inverses. So if we have a square matrix A, such as the one that we had before, the determinant of that matrix was actually negative 24,000. It was quite large. It was really scaling things quite differently. And the inverse of that matrix, we can actually just call linear algebra.inverse. Now, the inverse doesn't always exist. So for instance, when the determinant is equal to 0 right here, it doesn't have a specific inverse. This matrix did have an inverse, and here's what it's equal to. So the inverse of a matrix, you'll remember, is, let's say we had A times B, 2 matrices, and let's say they equaled some value y. If we multiplied each side by the inverse of A, so A, negative 1, AB, A, negative 1, dot product with y, these would form the identity matrix. So A times A inverse, so that would actually give us some values for B is equal to just A inverse y. And this is used a lot of times when we're doing numerical optimization techniques, or when we're trying to find a solution to a system of equations. And finally, eigenvalues. Eigenvalues, extremely important for linear algebra. We use them all the time in optimization. They're extremely important for figuring out the doing things like principal components analysis, figuring out sometimes part of the gradient. And so eigenvalues are something that's extremely important. And if you'll remember, eigenvalues essentially tell you what they give you a set of values and a set of vectors, and so each of those are associated with one another. So if I have a 3 by 3 matrix, and I can only do eigenvalues on a square matrix, but if I have a 3 by 3 matrix, I will have 3 different eigenvalues, and I will have 3 different eigenvectors. So this eigenvector is associated with this eigenvalue, and then the second eigenvector is associated with the second eigenvalue, and then the very last eigenvector here is associated with this eigenvalue. And so we'll talk more and more about eigenvalues as you progress through the program, but essentially they are things that we can calculate, and they have a geometric interpretation, which is if the matrix itself was some type of transformation that we were applying, the eigenvectors are vectors that if we drew them in the original space, transformed the space via a matrix operation, that vector would actually, it might be bigger or smaller, but it would be in the exact same direction. So it's telling us this vector always stays in the direction. Everything else will move. They'll change the different directions depending on what this transformation looks like, but the eigenvectors don't change inside the space. So that's a little bit of an intuition about that. We'll go over it more and actually show a lot of the practical uses for eigenvectors later on.